So we can make progress with our workshop, conference until last session. By my pleasure to introduce Konstantinas Pileckas, that you all know from Vilnius, and he'll speak about existence, non-stationary quasar solutions under minimal regularity assumptions. Please, Konstantinas, go ahead.
So thank you. First of all, I want to thank the organizers to organize this conference, this meeting, and inviting me. So I will speak about the Navier-Stokes solutions in the infinite stride pipe. So first, I want to say some words about the stationary case. This is well-known old results. So if we look for the solution of the stationary problem in a pipe, and we want to have the solution with a prescribed flux, then we can look at in the following forms. That the only component of the velocity field along the axis of the pipe is non-zero, and it depends only on the variables x prime on the section of the pipe. And then the pressure is linear in this case, and Q is some constant which depends on the flux F, and P0 is a free constant because the pressure is defined up to the constant. And yeah, okay. So and this solution can be found solving the just easy Poisson equation, and it has the following form. So this solution is called Poisson solution, and the Poisson solution is important in many industrial installations. For example, the oil pipes, and in some chemical industrial installation. Also in considering the blood flow. So it can be modeled by the flows in the thin tube structures, which was the talk of Sergei Nazarov. And the Poisson solution gives the asymptotics of the exact solution in the thin path.
Kost, you mean the talk at another conference, which was...
Yes, yeah, sorry.
2 days before.
Yeah, and it's also related to the Laderinskaya-Leray problem, which can be formulated as follows. Let us have some perturbed tube, and we have some exact solution with a prescribed flux, and the question is, does the solution at infinity tends to the Poisson solution? And this is the answer is positive in the case of the small fluxes. It was proved by Emick in the beginning of in the end of 80s, something like this, and it was also proved by I think beginning of 80s, and it was proved in the paper of Laderinskaya and Salonikov that there always exists a solution with a prescribed flux, and but this solution has an infinite energy dissipation, and for small fluxes it tends to the Poisson solution. This is the case for the stationary case. And the same questions could be posed for the non-stationary Navier-Stokes equations. In this case, the flux has to depends on the time, and of course it has to satisfy the compatibility condition. And again, we can look for the solution in the same form. The velocity vector has only one component, and the pressure is linear. But the coefficient Q now depends on T. So substituting it to the Navier-Stokes equations, we will get the following problem. And this is an inverse problem because the coefficient Q is unknown. The right side of the heat equation, which we get here, is unknown, and but we have the additional condition, the flux condition. So we have to find the solution U and Q such that this condition is satisfied. Now, so we can also consider the case when we prescribe this pressure drop Q, and then we have a usual heat equation, and we can find the solution by classical. But if we have the domain with several outlets to infinity, cylindrical outlets at infinity, and we have prescribed flux in each outlet, then because incompressibility of the fluid, the sum of these fluxes should be 0. And then if we prescribe in all outlets the pressure drop, then we do not know. So we don't know how to choose the pressure drops to have the fluxes to have the sum of fluxes is equal to 0. Therefore, anyway, we have to solve this inverse problem at least in one outlet to infinity. Okay, so in the stationary case, it's not a problem because the pressure drop Q is a constant and it's proportional to the flux F, and this nu is a viscosity coefficient, and K0 is a known constant. Okay, so we can define if the flux belongs to W12, we can define a weak solution of this inverse problem as the pair U and Q such that U depends to the space L2 W12 and its derivative in the space L2 and L2, and Q is an L2 space on interval 0, 2 and satisfies this integral identity. And this paper was considered by many authors in different functional setting and by different methods. So there are other references. So the papers of Hugo Berra da Vega and Galdi Robinson concern the time periodic case, and other papers. So it's the first paper was by Cannon in 1984, then by Peterman, and then by was my paper with Pileckas, my former PhD student, and then this Galdi and Robertson, my paper. So with different methods and different settings, it was proved the existence of this solution and the uniqueness of it. So also using this non-stationary Poisson solution was considered the Ladyghinsky array problem in the non-stationary case, and it was proved that the exact solution exists and tends to the non-stationary Poisson solution as x tends to infinity. In two-dimensional case, it was proved for arbitrary time interval, and in the three-dimensional case for small time interval, but for arbitrary, in both cases for arbitrary large fluxes. And so I will talk today about the case when the flux belongs only to L2. Then if we think about the parabolic problem, about the heat equation, we can expect that U is an infinity L2 and also in L2 W12. And Q is in L2, but I will show that it's not true. So this paper was this problem was considered in my paper with changes. And okay, so before giving the formulation of a very weak solution in this case, because the weak solution does not exist, Oh, why it's, yeah, I have to introduce some notation. So let us denote by S with the index f the primitive function f which is equal to 0 at 0. And multiplying the equation, then equation by eta and integrating by parts, we get the following identity. And now if we use that so the derivative of the primitive is equal to the of primitive of f is equal to f, and integrating by parts again, we can reduce this identity to the following one, where here are primitive of the gradient, and here is a primitive of function q. And so, and also, so since the L2 limit of sequence of primitive functions is not necessarily primitive of some function in L2, and we also cannot speak about the value of arbitrary function of L2 at some point, so we have to introduce some additional notation. So we denote what W12T, the closure of the set of smooth functions which are equal to 0 at the point T. And this is a dual to it. So, and so it can be proved the following lemma, that so it's easy exercise that any functional in this space can be represented in such form where h is some function in L2. And if we consider the duality with respect to L2 space, then it's easy to show that this space H will be primitive of small h tilde. So I will use the same notation by this space H. In general case, it's a functional, and H is not a primitive of some function, not necessary, but I will use the same notation, because this is primitive of this functional, just for convenience. Okay, so now we can say that a very big solution is a function u in such that u belongs to L2. Its primitive belongs to L2 W12, but we don't know that and do not assume that the gradient of function u itself exists in some space. Q belongs to this space of distribution of functionals, and U satisfies the initial condition and the flux condition, where flux satisfies this conditional 0. I put it in red because it's necessary to explain how we understand those conditions. And also it satisfies this integral identity for test function is in such space. So, and now how we understand first that the flux is 0 at 0. We assume additionally that 0 is the Lebesgue point of the flux, and that it's at this point this equality is equal holds, and so the value of f is equal to 0. And the same is for the initial condition. So we assume that, or we prove that 0 is the Lebesgue point of the L2 norm of U, and this equality holds. Now, the boundary condition is understood in the usual sense of traces, because if because the primitive belongs to this space, and it means that is in the W1 to 0 for almost all t, and then the trace of it is equal to 0 for almost all t again, and then the usual trace is equal to 0 for almost all x and t. So, okay, so the following, the main result is the following theorem, that if f belongs to L2 and f at 0 is 0, then for arbitrary t, the problem admits a very big solution, and the solution satisfies the following estimate and is unique. So, okay, what as in the case of the regular flux, the solution we can look for the solution in the form of Fourier series. If we take where we take the basis in the eigenfunctions of the Dirichlet Laplace operator, and then the functions WKN are given by this formula, where the function Q is still unknown because it is on the right hand side, but it's unknown. And so, okay, this is okay. So and we have also the flux condition. So we put this expression to the flux condition, and we get this equality where beta k are Fourier coefficients for the unit, and lambda k are eigenfunctions of the Laplace operator. So we see that UN has to satisfy the first kind Volterra integral equation, and if f has a derivative, we can differentiate it, and we get the second order, the second kind Volterra equation, which we know that is well posed in L2 space. But if we don't know the existence of derivative of f, we cannot differentiate this equation, and so the Volterra equation in this case is of first kind, and it's not well posed in L2 spaces. So we regularize it, adding this term with a small parameter epsilon. And now we have the second order equation, second kind Volterra equation. And for any epsilon and any n, we know the existence of the solution of it in L2. But of course, the constant in estimate will depend on n and epsilon, since the kernel of this equation depends on epsilon. Okay, so finally, summarizing, we find the weak solution, the approximate solution from this two equations, and we get that UN is of this form, and W has this expression where UN is the solution of second order, second kind Volterra equation. Okay, so now we have to get the a priori estimates, and to show that we can pass to a limit first by epsilon, then by n, and to get the weak solution. So this is more or less standard. So we multiply integral identity by such functions on depending on t, sum them by k. So we get this expression, and now the term is right hand side. We write q as a derivative of the primitive. Okay, and then integrate by parts. So we have then this equality. Sorry. This equality, and integrating by integrating by parts with respect to t, we reduce the previous quality to this form. And then we can estimate the right-hand side by the Young inequality, and we get this this estimate with a arbitrary small delta between. So now, but in the right-hand side we have the unknown term. No, sorry, I lost something. Yeah, we have this unknown term because this is a primitive of the function q, which is not estimated. To estimate this function, we multiply, or we take in the, okay, we take the solution of the Poisson equation, and this solution can be expressed in the Fourier series again, and so we can multiply equations, equalities 13 by coefficients, Fourier coefficients a k of this function, and sum it over all k's. So we get this equality here. And on the other hand, we can multiply the Poisson equation by un, and we get this equality. But we know this is a flux. So in this flux, from our integral equation follows that is equal to this sum. So we finally express the qn from these two equations, and we get this relation, and integrating it by t, we get that the primitive of q is equal to this right-hand side. So then, just taking sphere of both parts, we can get this estimates, and we estimate the primitive of q over the norm of L2 norm of u, and so substituting it to the, I'm sorry, I think it should be, no, it's okay. So substituting it to the previous inequality, we get now, so here was the norm of primitive of q. Now it's estimated by the norm of u with a small parameter delta, and so we can get all estimates of the approximate solutions over the flux in the terms of flux. So flux and primitive of flux. So, and this we see that this now the approximate solutions satisfy this identity for any function eta, which is the linear combination of eigenfunctions uk with the coefficients depending on t from W1 to, and such that at capital T they are equal to 0. And this sequence is bounded, uniformly bounded with respect to n and t. So first we take some sequence epsilon L, which tends to 0, and such that the sequence with a fixed n is convictly weakly convergent in the space L2 0t L2 sigma, and the sequence of qn epsilon L converges weakly in this space of functionals, and we can pass to the limit in the integral identity, and we get such identity for the limit function un and sqn. And we have to show also that its function satisfies the flux condition. But so the integral identity can be written in the following way. So if we integrate it by t, we get here the primitive of q, and in the right hand side the primitive of f. So such sequence is obviously bounded in L2, and we may so assume that we have choose the subsequence which is weakly convergent to some function phi in L2 0t. But then the sequence of primitives will be convergent uniformly for any t. And we get that the primitives converge strongly in L2. And so from 23, from this equality, we get then that this is equal to epsilon L, the norm of SQ and epsilon L, and these norms are bounded, uniformly bounded. So when epsilon L goes to 0, we get that this is 0. Therefore, passing to the limit, we get this for almost this equality for almost all t. So differentiating it, we get that the flux of un is equal to f. And now we also have to pass to the limit by n. When n goes to infinity, also we choose weak convergent subsequences, and we pass to the limit. We get that this identity 24 is true for any function eta which has this form, but such functions are dense in this space of in the space of test functions. Therefore, the 24 remains valid for any function eta for any test function eta, and so u and q are the very weak solution of our problem. Now we have to show that u satisfies the initial condition. So proving this estimate for estimate 19, we have got such estimate, this estimate, and then so estimating by Cauchy-Schwarz inequality, just this integral, we get this. So everything is estimated in so the L2 norm of u is estimated in the term of f of L2 norm of f for arbitrary upper limit integration limit t, and constant is independent on t. Therefore, dividing both sides by t, we get this, and we know that this is that the right hand side tends to 0 as t goes to 0. So we get that also the left hand side goes to 0, and we prove that that this is that the bound initial condition is satisfied. So we don't have here the continuity of this norm at when t goes to 0. We only have that this is 0 in the sense of the Lebesgue points. And to have the continuity, we need to assume that the flux F belongs to some W epsilon 2 with any positive epsilon. Then it's possible to prove the continuity, but I will omit this. So, okay, now also we can prove the uniqueness. So if F is equal to 0, so we can take in the integral identity such test function eta, and substituting we get the following equality. And since the flux is equal to 0, also the flux of the primitive function will be equal to 0. And by Fubini theorem. And so we get this, and we immediately get that the solution, that the u is equal to 0. Now we have to show that this function is q is equal to 0. So s of q is equal to 0. So the function is equal to 0. And we take now eta. We have that this integral now is equal to 0 because the left-hand side is already is proved that equal to 0 because u is 0. And now we take such function as a test function where u is again the solution of this Poisson equation. And since this integral is non-zero for this function, we get this equality from which it follows that this integral is equal to 0 for any b in C0 infinity, and this means that SQ is equal to 0. So we have proved the uniqueness, and now I want to show that this class of solutions which was introduced was not some fantasy. That so I will show the example of the function of the flux F when the solution is just like this and not better. So first of all, I want to say the following. So if we have the flux F in which is time periodic, and we consider it on interval minus pi pi, and if it's time periodic function, then the solution, so the SQ, so primitive of the Q, will be also time periodic. They can be expressed by Fourier series, and the coefficients of F and S are related by such formulas, where AN and BN are expressed by the integrals of phi-n and psi-n, where phi and psi-n is the solution of following elliptic problem. And this was proved in the regular case by Galdi and Robertson, and in this non-regular case, the proof is just exactly the same. And the solution and U then is expressed by the following formula, where MSN and MCN are given by this formula. So it follows from the paper of Galdi. Okay, so let us take the flux F. So first of all, we consider a problem on the interval 0 square root of 2 and take F in this form. The flux is equal to this. Then where epsilon is arbitrarily larger than 0. Then F belongs to L2, but F does not belong to any W space with any delta. And then we compute the coefficients of function Q, the primitive of Q, which will be given now by such formulas. This is direct computations. Also the coefficients of U, Fourier coefficients of U, and these coefficients AN and BN, which are participating in these definitions. And so it's so we get that these coefficients have this form where PE are sixth-order polynomials with some constant coefficients which can be computed, and then we have the following estimates for these coefficients, and from these estimates it's easy to see that the corresponding Fourier series for U belongs to L2, but its gradient does not belong to L2 space, and also, but gradient of the primitive is in L2. So it's just, and also it can be shown that U does not belong to any W epsilon 2 with any epsilon. So the class of solutions which was introduced is just exact class which is needed to study this problem for the flux in the space L2. So that is all. Thank you. Thank you, and I want to congratulate again Theodor Alexeyevich with his birthday, and to wish him all the best in the future. So thank you for attention.
Okay. So thank you very much for your interesting talk, and I understand, Kostas, that this is a recent result, not yet published. Is that right?
It's published already. Published.
Oh, can you give us the reference?
Last year? Yeah, last year.
Oh, can you give us the reference, because I was not able to see in your slides. You have the reference?
Not in slides, but I can.
You can send me later. Okay,
Yeah,
please.
I can send you. Yeah, so.
Okay, I did not want just to ask questions, just
yeah.
Finalize your thing. Okay, so please open now to questions. So please, who wants to?
Okay, I have a question. You said that if you could differentiate the Volterra equation for Q, then you could obtain the second type,
Yes.
second kind equation. But why cannot you do this in the negative Sobolev space?
So. So we get that the right-hand side is then in the negative.
Yeah, and to solve this equation in the negative Sobolev space.
Is it? I don't know. Maybe it's possible, but I don't know.
Yeah, because in fact you in the result you obtain Q just in the negative Sobolev space.
Yes.
Maybe it is simpler.
Maybe it's simpler. Maybe. But do we know the probability of the Volterra equation?
No. Well, it is a question. Yeah. I am not expert in integral equations, but
I want to say that in both cases, in smooth case and in non-smooth case, you cannot use a priori estimates, so which we get from the Volterra equation, because the kernel is the infinite series will be the limit, and so the a priori equation is necessary to obtain from the heat equation.
Okay.
And this is only for to get the approximate solution. Huh? So this.
Yes, I see.
Well, okay. So, any more questions or remarks?
If we differentiate equation 11 with respect to t, we obtain q outside of integral because exponent when tau is equal
it is just what was said.
is,
But we cannot differentiate because M has no
and I think there is no problems because after integration we obtain the second order Volterra equation.
Yeah,
Uh,
but the
so-
question is whether it is possible to differentiate the function without derivative.
Well, distributional
There
sense
are
in T.
no problems with
Okay,
respect
but I
to
think, well,
differentiate.
Yeah.
But the right-hand side has no derivative. We cannot differentiate it.
okay.
And I see there is no problems to find Q.
No, okay, maybe.
Maybe I think it's an interesting challenge question. In fact, I could also give my opinion, but I think we should not start the discussion here. Also, more questions or more comments, because it's well. Okay, so we thank you again. Thank you, Costas, and don't forget to send us a reference. Thank you. And I think now we are about to end this.